e to the negative 0. Again, since anything to the 0 power is equal to 1, this simplifies to 1/2 times 1 plus 1/2 times 1, or just 1/2 plus 1/2, which is 1. 1 equals 1, so this condition is met as well.
And thus, we have verified that y equals 1/2 e to the x minus 1/2 e to the negative x is indeed a unique differential equation, y double prime minus y equals 0, and the two given initial conditions.
Part 2. Solving first-order differential equations.
Now we're going to get to the heart of this differential equation stuff. To get you into the mood for the mind-bending experience ahead, we're going to play some subliminal relaxation music. Just close your eyes and focus inward.
I find differential equations to be fun and easy.
Now that you're nice and relaxed, let's dive in. What we're going to learn now is a boatload of techniques for solving first-order differential equations. Remember, first-order differential equations are equations where the highest derivative appearing in the equation is the first derivative.
As we go through each of the following techniques, keep in mind that the best and most efficient method for solving a differential equation will depend on the type of equation you have. At some point, you will be faced with a differential equation all by its lonesome, and you'll have to identify what type of equation it is so you'll know which technique you need to use to solve it. But remember, if you get lost or confused, you can always rewind the tape and watch it again, or stop the tape and eat a carb-loaded energy bar.
Section A. Separable differential equations.
The first type of differential equation we will cover is called a separable differential equation. These equations are also sometimes called variable separable because in essence that's what we're doing with them, separating the variables.
Note to self, separate the variables.
To show you how this separable stuff works, take this sample equation. dy dx equals f of x times g of y. This is the form for a variable separable differential equation. This equation is separable because we can, with the help of a little elementary algebra, get all the x's with the dx and all the y's with the dy. The way we do this is to put all the y terms on the one side of the equation and all the x terms on the other side of the equation.
To separate the variables here, we first multiply both sides of the equation by dx. This cancels the dx on the left and moves it over to the right side to be with the f of x. Now we've got that g of y getting in the way on the right side. To move the g of y over to the left, we simply divide both sides by g of y. This gives us 1 over g of y dy equals f of x dx, and wham! The variables are separated.
We say the variables are separated because, as you can see, all the y's and dy are on one side of the equation, and all the x's and dx are on the other. To get the final solution, we would just integrate both sides of the equation independently. Now let's work through a bona fide example.
Here's a bona fide example. Solve the differential equation dy dx equals 2xy. Here's a tip. Separate the variables.
Given this equation dy dx equals 2xy, we can easily separate the variables. If we multiply by dx to get dy by itself on the left side of the equation, we get dy equals 2xy dx. We're almost finished, but remember, we want all the x's with dx and all the y's with dy. So to get this pesky y over to the left side with dy, we divide by y and get 1 over y dy equals 2x dx. Now the variables are separated, and we have an equation that can be easily integrated.
Integrating the left side, remember the rule from calculus that tells us that the integral of 1 over a variable is the natural log of that variable. So the integral of 1 over y dy is the natural log of y. Remember this rule for the natural log. We'll use it all the time. Tattoo it on the insides of your eyelids, or whatever. Just remember it.
Integrating the right side, we apply the power rule for integrals, which gives us x squared plus c. Don't forget the c. You may as well tattoo that on your eyelids as well, because the arbitrary constant will never go away. So our final answer is the natural log of y equals x squared plus c.
So we've solved a variable's separable differential equation.
Or have we?
There is one more step we must do if we want to be thorough. To really have the most complete answer in addition to what we've already done by separating the variables, we must solve for y. This is called an explicit solution because the dependent variable y is expressed solely in terms of the independent variable x and constants. What this means in plain English is for y.
To solve for y in our solution here, we need to get rid of the natural log. We do this by exponentiating. To exponentiate, we raise both sides of the equation to the base e. We do this whenever we need to get rid of a natural log, because we all remember the rule from calculus that tells us that e to the natural log of a variable equals the variable.
Exponentiating both sides of the equation, we get e to the natural log of y equals e to the x squared plus c. Since e to the natural log of a variable equals the variable, we've just got a little old lonely y on the left side. So we have y equals e to the x squared plus c. Now for the right side, we've got to do a few more tricks to whittle this thing down.
First, recall one of the basic rules of exponents. E to the a plus b can be rewritten as e to the a times e to the b. For our problem, e to the x squared plus c can be rewritten e to the x squared times e to the c.
Now look what we can do here. The second term, e to the c, is a number raised to a constant. Remember, e is, after all, a number. 2.718 approximately, and c is a constant. So the whole thing, e to the c, is also a constant. Let's represent this constant with a different letter, so we don't get confused. We'll call it k for constant. So the right side of the equation is now just k times e to the x squared. Putting it all together, we get y equals k times e to the x squared. And that, my friends, is the explicit solution for our first order, variables separable differential equation.
Breaker, here's what we just did in that problem. We were given dy dx equals 2xy. We separated the variables and got 1 over y dy equals 2x dx. Integrating, we got the natural log of y equals x squared plus c. Solving for y to get the explicit solution, we exponentiated and got y equals e to the x squared plus c. Consolidating the constants, we got y equals k times e to the x squared. And that was our answer. Out.
Notice that in our last example, the final answer, y equals k times e to the x squared, has a constant in it. We can leave our answer in this form because we weren't given any initial condition or constraint that would allow us to find a specific value for the constant k. Now let's move on to a more complex problem that does give us an initial condition to deal with.
All right, brave comrades. Our task now is to find the solution for the differential equation dy dx equals y squared plus 1 with the constraint y at 1 equals 0. This is an initial value problem, or IVP, with the initial condition that when x equals 1, y equals 0. Any suggestions on how to begin?
Here's a tip. Separate the variables. Separate.
Well, since the cat is out of the bag, let's go ahead and separate the variables. Step 1 is to get the y's with the dy and the x's with the dx. To do this, we multiply both sides by dx. This cancels the dx on the left and moves it to the right. Now we need to move the y squared plus 1 to the left, so we divide both sides by y squared plus 1, leaving us with 1 over y squared plus 1 times dy equals dx.
Now that we have the variables separated, step 2 is to integrate this baby. In order to integrate this equation, we just integrate both sides individually.
Looking at the left side, you may be wondering just how to integrate this sucker. Well, recall that old integration rule that states that the integral of 1 over a variable squared plus 1 equals the arctangent of that variable.
Oh, that old rule. How silly of me. Of course I remember that crazy old rule. I haven't slept for 72 hours.
Insert card alert. Insert card alert.
So, following this crazy rule, on the left side we get the arctangent of y. Now integrating on the right, we just get x. And what else? The c! The plus c! Don't forget that doggone c.
So, our solution is the arctangent of y equals x plus c. Remember that the arctangent can also be written as the inverse tangent, so you could also write the answer like this.
Hey, didn't we have one of those, initial conditions to deal with?
Yeah, why don't you cut the chat and deal?
Remember, we were given y at 1 equals 0. So step 3 is to plug x equals 1 and y equals 0 into our solution and solve for c. Plugging in, we get the arctangent of 0 equals 1 plus c. The arctangent of 0 is 0, so c equals negative 1.
Taking all of this information together, we can grind out our final answer. Subbing the value c equals negative 1 into our solution gives us the arctangent of y equals x minus 1. Now, it's acceptable to leave your answer in this form, but in some instances your professor may ask you to solve for y. If so, then the last step here, or step 4, is to put our solution into explicit or y equals form.
To solve for y here, we need to take the tangent of both sides of the equation. Now, using trig properties stored deep in our gray matter, we know that the tangent of the arctangent of y is simply y. So we end up with y equals the tangent of the quantity x minus 1. And that is the unique solution to our variable's separable initial value problem.
Breaker, here's what we did. We were given dy dx equals y squared plus 1 with the initial condition y at 1 equals 0. Separating the variables, we got 1 over y squared plus 1 times dy equals dx. Integrating, we got the arctangent of y equals x plus c. Solving for c using the given initial condition, we got the arctangent of y equals x minus 1. Then, solving for y, we got the final answer of y equals the tangent of x minus 1. This is Recap Pap, over and out.
A differential equation is separable if it's in a form that allows you to get all the x's with the dx and all the y's with the dy. If this is the case, then the equation can be integrated using techniques we learned in calculus. Here are the 4 steps we outlined for solving a variable separable differential equation with a given initial condition.
Step 1. Get the y's with the dy and the x's with the dx to separate the variables. Step 2. Integrate each side of the equation using the integration rules you learned in calculus. Step 3. Plug any initial conditions into the solution to find a value for c. And step 4. Put the solution into explicit form, if possible, by solving it for y. And that's all there is to solving a variable separable differential equation.
Section B. Exact differential equations.
Now that we've learned how to solve separable differential equations, we're ready for another type of differential equations, exact differential equations. This technique is a bit more complex than the last one, so try to stick with us here.
Now, with exact differential equations, we're dealing with equations in the form m of xy dx plus n of xy dy equals 0, where separation of variables does not apply. In order to solve an equation like this, we need to do some creative visualization. The technique we use here may seem like an odd roundabout way to solve an equation, but it works, and that's why we like it.
First of all, let's say we've got an equation in this form. M of xy dx plus n of xy dy equals 0. We work on the hope that the left-hand side of this equation is the total derivative of some mystery function out there, which we'll call f of xy. So, we assume that f prime of x equals m of xy dx plus n of xy dy.
Note to self, assume that f prime of x equals m of xy dx plus n of xy dy.
Basically, the method to solve an exact differential equation revolves around finding that mystery function f of xy, whose derivative, we're assuming, equals the equation we were given. How do we do that? Well, we integrate. What we've got is an equation that corresponds to f prime of xy equals 0. Integrating both sides, we get the mystery function f of xy equals a constant c. And that's what we're looking for. Make absolutely no sense? That's okay. Just hang in there. It'll start to come together as we go along.
Another thing about the mystery function f of xy. Using the chain rule, we can say that the total derivative of f equals its partial derivative with respect to x times dx plus its partial derivative with respect to y times dy.
Okay, so still using that creative visualization of ours, if the derivative of f is equal to m of xy dx plus n of xy dy, and also equal to the partial derivative of f with respect to x dx plus the partial derivative of f with respect to y dy, then we can set up the equality m of xy dx plus n of xy dy equals the partial derivative of f with respect to x dx plus the partial derivative of f with respect to y dy. Now we're in business.
Anyway, from this equality, we can equate the parts on opposite sides of the equal sign to each other. So, we conclude that m of xy equals the partial derivative of f with respect to x, and n of xy equals the partial derivative of f with respect to y.
Why go to all this trouble? Well, here's the point of this whole discussion. Not every equation that looks like an exact differential equation is actually an exact differential equation. So, from the equalities we just found, we can devise a test to determine if a particular differential equation is of the exact form. Once we determine that, then we can go ahead and solve the baby.
Going back to our two equalities, we can find a connection between them by taking the partial derivative of each one. Watch this. Taking the partial derivative of m of xy with respect to y, we get the partial derivative of m with respect to y equals the second partial derivative of f with respect to y and x. Taking the partial derivative of n of xy with respect to x, we get the second partial derivative of f with respect to x and y also. Since the second partial derivatives of f are the same, we can see that the partial derivative of m with respect to y equals the partial derivative of n with respect to x.
Why do we care that these two derivatives are equal? Well, this is the test to determine if an equation of the form m of xy dx plus n of xy dy equals 0 is an exact differential equation. If the two partial derivatives, m with respect to y and n with respect to x, are equal, then the differential equation is exact. We'll show you how to apply this test in just a second.
Let's do an example and learn through experience. Solve the differential equation 2x plus 3y dx plus 3x plus 5y squared dy equals 0. Where do we begin? Well, first notice that it's impossible to separate the variables here. So let's test this problem and see if it fits the requirements for an exact differential equation.
I have it from very reliable sources that it will. But you did not hear that from me. Now run out of here, kid.
Let's apply the test. Remember, we said that a differential equation is of the exact type if 1. It's in the form m of xy dx plus n of xy dy equals 0, and 2. The partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. Notice that up here in the general form, the m part is with the dx, but down here, we're taking its derivative with respect to the y. And, on the other hand, see that the n is with the dy, but down here, we're taking its partial derivative with respect to x. Don't let that mix you up.
First, we need to see if our equation 2x plus 3y dx plus 3x plus 5y squared dy equals 0 is in the right form. Comparing it to the general form, m of xy dx plus n of xy dy equals 0, we can easily see that m is the first part here, the 2x plus 3y, and the n is the second part, the 3x plus 5y squared. So, the equation's in the right form, and we've got our m and n. Now that we know what m and n are, we need to take their partial derivatives. Remember, when taking a partial derivative, we hold all the other variables constant, except for the variable we are taking the derivative with respect to.
We'll do m first. Now, for the exact test, we are taking the derivative of m with respect to y, so that means that we treat y as the variable and x as a constant. So, here we treat 2x as a constant because it does not contain a y term, giving us 0 as its derivative. The derivative of the second term, 3y, is just 3, so the partial derivative of m with respect to y is 0 plus 3, or just 3.
Now, let's do the n part.
Alright, for the n part, we are taking the derivative with respect to x, so that means that we treat x as the variable and y as the constant. The derivative of the first term, 3x, is just 3. For the second term, we treat 5y squared as a constant, giving us 0 as its derivative. So, the partial derivative of n with respect to x is 3 plus 0, or just 3.
Our differential equation passed the test. The differential equation is in the proper form, and the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. They're both 3. The equation is therefore of the exact type and can be solved by the exact differential equation technique. So, here goes.
Okay, let's pause here for a second. We just applied the test and successfully determined that this equation is indeed exact. But that's just the tip of the iceberg. Now we need to solve the equation.
Remember, our exact differential equation is 2x plus 3y times dx plus 3x plus 5y squared times dy. The first step in solving the equation is to integrate. But here's the interesting thing. We only need to integrate one part of the equation, either m or n. Why? Well, think about it this way. Remember earlier we established that m equals the partial derivative of f with respect to x, and n equals the partial derivative of f with respect to y? Well, that means that the mystery function f equals both the integral of m with respect to x and the integral of n with respect to y. So, integrating either one will give us what we want. How do we choose which to integrate? Well, there is a very sophisticated process.
1 potato, 2 potato, 3 potato, 4!
Actually, the best thing to do is look at m and n and pick the one that looks easier to integrate. I mean, we're not idiots here. Let's go the easy way. In our example, m and n are both fairly simple to integrate, so we'll just pick one randomly.
5 potato, 6 potato, 7 potato, or...
So, m it is. We integrate m partially with respect to x. Why with respect to x? Because its partial derivative is taken with respect to x. If we had chosen to integrate n, we would have done so with respect to y for the same reason.
To integrate 2x plus 3y with respect to x, we use the power rule for integration. The first term, 2x, becomes 1/2 times 2x squared, or just x squared. The next term, 3y, is treated as a constant because it has no x in it, and we are integrating with respect to x. Therefore, it just becomes 3xy. Now, normally we would add an arbitrary c to the end here, but since we're treating y as a constant for this integration, we need to write the constant of integration as a function of y, c of y. We'll call this a c function because it will always be c of x or y, depending on whether you choose to integrate m or n. So, the partial integral of m with respect to x is x squared plus 3xy plus c of y.
Since m equals the partial derivative of f with respect to x, going backwards and taking the partial integral, which we just did, will give us the function f. So the answer we just got, x squared plus 3xy plus c of y, equals the mystery function f. Well, sort of. We've still got to figure out what to do with that c of y. So step 2 is to find the c function, in this case, c of y.
To find the unknown c of y, we need to equate it with something we do know. Remember that n is equal to the partial derivative of f with respect to y. Since we just found that f of xy equals x squared plus 3xy plus c of y, we can go backwards and take its partial derivative with respect to y and set it equal to n. Then we'll be able to find c of y. Trust me, it'll work out. You'll see.
Taking the partial derivative of x squared plus 3xy plus c of y with respect to y gives us 0 plus 3x plus c prime of y, or just 3x plus c prime of y.
Setting the partial derivative of f with respect to y equal to n, we get 3x plus c prime of y equals 3x plus 5y squared. Now we can solve 8. Here is a point where we can check that we've done everything correctly so far. If the x terms on each side cancel each other out, then we're good to go. If not, then we've got a problem. But here it all checks out. The 3x's on each side will drop out and go to the races together, And we've got what we're looking for. C prime of y equals 5y squared.
To get c of y, we just need to integrate c prime of y with respect to y. Integrating 5y squared, we get 5/3 y cubed. Don't worry about a constant of integration here. It'll show up later. You'll see. So, c of y equals 5/3 y cubed.
Our final step, now that we have c of y, our c function, is to plug it into the mystery function f that we found earlier. Plugging in, we get f of xy equals x squared plus 3xy plus 5/3 y cubed. Since we know that the general solution is given as f of xy equals a constant, then we can rewrite this as x squared plus 3xy plus 5/3 y cubed equals c. There's where the constant shows up. And that, my good friends, is the general solution of the differential equation.
Breaker, here's what we did. We started with the equation 2x plus 3y dx plus 3x plus 5y squared dy. First, we tested to see if the equation was exact. We let m be 2x plus 3y and n be 3x plus 5y squared, and found that the partial derivative of m with respect to y and the partial derivative of n with respect to x were both 3. So the equation passed the test. We then partially integrated the m part with respect to x and got the mystery function, f, to be x squared plus 3xy plus c of y. To find c of y, we took the partial derivative of f with respect to y, set it equal to n, and found that c of y equaled 5/3 y cubed. Plugging this back into f, we got our final solution of x squared plus 3xy plus 5/3 y cubed equals c. Over and out.
Again, we've been on a long roundabout journey to get our answer, but that's just the way it goes with differential equations. A lot of paperwork, killing a lot of trees, but hey, now you got techniques for solving count 'em, two types of differential equations: variable, separable, and exact differential equations. But before going on to another technique, let's take a few minutes and review the steps for solving an exact differential equation.
A differential equation is of the exact type if two conditions are met. First, it has the form m of xy dx plus n of xy dy equals 0. And second, the two partial derivatives, m with respect to y and n with respect to x, are equal. If they are equal, then we've got an exact differential equation. If not, then we've got something else on our hands.
Once you have determined that an equation is of the exact type, there are three main steps to find the solution. The first step is to choose one part of the equation to integrate, either m or n, whichever is simpler. This integration gives a form of the mystery function f of xy that we're looking for. However, at this point, it will contain a c function that we need to solve for. So, the second step is to solve for the c function. To do this, take the partial derivative of f of xy and set it equal to the other function, m or n. And finally, now that we have solved for the c function, step 3 is to sub it into f of xy, and the solution to the exact differential equation is then obtained as f of xy equals a constant.
One last point. Realize that the choice you make in the first step, whether to integrate m or n, will determine how you integrate and differentiate the rest of the problem. In our example, we chose the m part, so we integrated with respect to x. Then, to solve for c of y, we differentiated with respect to y. If you chose to integrate the n part at the beginning, then all of this would be reversed. It will all make sense when you get into a problem. You'll see. Now let's move forward.
Section C. Linear first-order differential equations, or solution by an integrating factor.
So now we're ready for the big time. Linear first-order differential equations, which are solved using an integrating factor. Wow! But before we move one step further, let's define what an integrating factor is. Then look at what it can do for us. Because you know, what we're really interested in is what's in it for us.
An integrating factor is basically something that you multiply an equation by to change it from a form you don't like into a form you do like. Now, you may want to use an integrating factor on your roommate, but actually, it's most useful on certain types of differential equations.
To apply this integrating factor method, you need a linear first-order differential equation. A linear first-order differential equation takes this form. dy dx plus p of x times y equals q of x.
Let's take a look at this baby and see what makes it so special. First, notice that it's a first-order differential equation because the highest derivative in it, dy dx, is a first derivative. Second, notice that there's nothing multiplying the first term, the dy dx term. In other words, the dy dx term has a coefficient of 1. Third, notice that the second term, p of x times y, is just a function of x times a lonely old y. And finally, notice that on the right-hand side, we just have a function of x only, q of x. No y to be found. Make note of it.
Now, not every equation that you'll be handed will be in this dy dx plus p of x times y equals q of x form. But that doesn't mean that you're bum out of luck. In those situations, you can sometimes manipulate the equation to get it into a more user-friendly form. Check out these examples.
This equation, y prime plus 5xy equals 5xe to the negative x squared, is in the right form. Remember that y prime is the same thing as dy dx, so our first term is a-OK. The second term, 5xy, is just a function of x, 5x, times y. So 5x is our p of x, and y is just y. So the second term also checks out. Now that ugly term on the right side, 5xe to the negative x squared, also checks out because it is a function of x only. No meddling y's stuck in there to ruin the day, so this guy fits the bill.
Now let's mess with our perfect little equation for a minute. Suppose we change the 5xy in the second term to a 5xy squared. Well then, that'd be the end of that. This equation is no longer in the right form. Also, we could bungle everything by inserting a y to the 5xe to the negative x squared on the right, making it a function of x and y. So as you can see, these equations are very temperamental.
Now take this equation. xy prime minus 3y equals x cubed times e to the negative 2x. Everything looks all right here, except for that xy prime in the first term. We know that we can rewrite the y prime as dy dx, and that's okay. But we're still stuck with that dang x. So close, but yet so far. But not so fast. We can still make things right. If we simply divide through by x, we get dy dx minus 3 over x times y equals x squared times e to the negative 2x. Now we're home free. We've got dy dx all alone in front, and here's our p of x, and here's our q of x, and all's quiet on the western front.
What we did with that last equation, dividing through by the coefficient of the first term, is a common way of getting an equation in the right form. If at first things don't look right, see if there's anything you can do algebraically to bring the equation into the proper form.
Okay, so we've looked at the form a differential equation needs to be in for this integrating factor technique, but we haven't talked about how to get the integrating factor itself. Where does it come from? Well, there's a very simple answer to this question. Integrating factors grow on trees.
Bitter. Once you have your equation in the proper form, dy dx plus p of x times y equals q of x, then the integrating factor is practically staring you in the face. To find the integrating factor, take the p of x term and put its antiderivative as the exponent of e. In other words, the integrating factor, or I of x, is e to the integral of p of x dx. This sounds like an odd thing to do, but it makes it possible to solve the differential equation.
Once we've looked at our p of x term and found our integrating factor, I of x, we multiply both sides of the equation by it. When we do this, an interesting thing will happen. You won't see it happen here, but trust that it will happen when you've got a problem with real numbers.
On the left side of the equation, after multiplying by the integrating factor, we'll get the reverse of the product rule for derivatives, which can be written as a derivative of the quantity I of x times y. On the right, we get q of x times I of x. Now, we can integrate each side of the equation separately to get the solution. Sound confusing? Well, it is. So try it out on a problem.
Let's find a solution for the equation y prime equals y plus x plus 5. This is a linear equation of first order, but it's not in the right form for our integrating factor method. We need to have it in the dy dx plus p of x times y equals q of x form. If you look closely, you'll see that we have all the right components, just not on the right sides. If we subtract a y from both sides, we get y prime minus y equals x plus 5.
Now we can see that the equation matches up with our form. The y prime is the dy dx, the minus y is the p of x times y, and the x plus 5 is the q of x. From this, we can easily recognize that p of x equals -1 because that is the coefficient of our y term. Now we're ready to build our integrating factor.
Remember, the integrating factor, I of x, equals e to the integral of p of x dx. Our p of x is just -1, so our integrating factor equals e to the integral of -1 dx. Computing the integral of -1 dx separately, we get -x. So the integrating factor is e to the -x.
Now that we've got a real live integrating factor, what do we do with it? Well, we multiply both sides of the equation by it. So let's try.
The original equation is y prime minus y equals x plus 5. We determined the integrating factor to be e to the -x. Multiplying both sides of the equation by e to the -x, we get e to the -x times y prime minus e to the -x times y equals e to the -x times the quantity x plus 5. Looks like a jumble, but it's about to get a whole lot less complicated. Watch this.
So here's what we got. Now the next step would be to integrate each side of the equation. But before we do that, there's a nifty trick we need to do. Look at the left side of the equation. Look very closely. If you use your imagination, you can see that what we have here is the result of a product rule. These two terms represent what you get after you take the derivative of the product of two functions, in this case, e to the -x and y. Here, we'll show you.
Say we've got e to the -x times y. Using the product rule, the derivative of the product of these two functions is the derivative of the first, -e to the -x, times the second, y, plus the derivative of the second, y prime, times the first, e to the -x. If you rearrange this a little bit, you'll notice that it matches up with the left side of our equation.
Going back to our equation, we can replace the left side with the derivative of e to the -x times y. We use the prime sign there to indicate the derivative.
Just a quick word about this product rule stuff. When multiplying by an integrating factor with a problem of this fashion, you should always have a product rule at this point. If you don't, then you've bungled somewhere. So you need to get good at recognizing the product rule. It'll pop up often.
So, we've found our integrating factor, we've multiplied by the integrating factor, and we've done a product rule replacement. Now we're ready to integrate.
Taking the equation as we now have it, our next step is to integrate each side. To do this, we integrate each term individually. On the left side, the integration is very easy. The integral of the derivative of e to the -x times y is just e to the -x times y. Do you see that here? We have the integral of a derivative. These two operations, integration and differentiation, cancel each other out. So, we're done with the left side. The right side, though, is another matter.
The two integrals on the right are not so easy to evaluate, especially that first one, the integral of x times e to the -x. Let's focus on this one first.
Since this is the product of two functions, we can't use the power rule for integration here. Also, note that a typical u du substitution will not work here either. So, we need to pull another integration technique out of our memory banks. Integration by parts fits the bill here because the integrand is the product of two functions, both of which can be integrated easily.
Recall that to use integration by parts, we assign one function as u and the other as dv, which is the derivative of some function v. We differentiate u to find du and integrate dv to find v. Once we have values for u, v, du, and dv, we plug them all into the formula for integration by parts, which is u times v minus the integral of v times du. Now, you should know all of this from calculus, but I'm sure this little review won't hurt.
To begin, we'll set u equal to x. Then, by differentiating, Find du to be dx. Next we assign dv to be e to the negative x dx, and by integrating, find v equals negative e to the negative x. Now that we have these values, we can plug them into the formula and see if it holds water.
The formula for integration by parts is u times v minus the integral of v times du. Plugging in the values we just found, we get x times negative e to the negative x minus the integral of negative e to the negative x dx. Now we just need to integrate the last part, which is easy enough because the integral of negative e to the negative x is just e to the negative x. Therefore, the integral of x times e to the negative x dx is negative x times e to the negative x minus e to the negative x.
Now back to our equation. We just found the first integral on the right side. Now we have to find the next one, the integral of 5e to the negative x. This one's not so hard, so we'll do it right here. The integral of 5e to the negative x is just negative 5e to the negative x. Now we've got all the pieces.
Putting the pieces together, we get e to the negative x times y equals negative x times e to the negative x minus e to the negative x minus 5e to the negative x plus c. Simplified, the right-hand side is negative x times e to the negative x minus 6 times e to the negative x plus c.
Note to self, don't forget the C's.
Now one last step. We can solve for y by dividing through by e to the negative x and then simplifying. This gives us y equals negative x minus 6 plus c over e to the negative x. This can be simplified to y equals negative x minus 6 plus c times e to the x. And that's the general solution to our differential equation.
Breaker, here's what we did. Our problem was y prime equals y plus x plus 5, which we put in proper form as y prime minus y equals x plus 5. We then found the integrating factor, I of x, to be e to the negative x. Multiplying both sides of the equation by I of x, we got e to the negative x times y prime minus e to the negative x times y equals e to the negative x times x plus 5. We did a product rule replacement on the left side and got the derivative of e to the negative x times y equals e to the negative x times x plus 5. Integrating both sides and solving for y, we got y equals negative x minus 6 plus c times e to the x. Over now.
And yet, another technique to tack onto your wall, solution by integrating factor. This technique is sometimes referred to as linear first order, because that's the type of equation it applies to. At any rate, it's a technique you'll need to know. So before going on, let's review the main steps for solving a differential equation of this type.
An integrating factor is a factor that you multiply an equation by to change it into a more workable form. To apply this integrating factor method, you need a linear first-order differential equation of the form dy dx plus p of x times y equals q of x. The integrating factor, or I of x, is formed by putting e to the integral of p of x dx. Once the integrating factor is formed, we multiply both sides of the equation by it. This will put the equation into a form where we have the reverse of the product rule for the terms on the left. From there, the equation can easily be integrated using the techniques we learned in calculus. That's it.
Section D. Which technique do I use?
At this point, you may be feeling overwhelmed or confused by the sheer number of techniques to solve what seem like similar problems. Well, there are significant differences you need to recognize so that you can select the proper technique to solve a given differential equation. But first, to relieve some of the anxiety, here's another dose of subliminal relaxation music. Just close your eyes and focus inward.
Now it's time for everyone's favorite quiz show, Name That Equation!
Hello, and welcome everyone to Name That Equation. I'm your host, Lance Joey Bickford. Here's how the game works. Our two contestants will be given a differential equation, and they must determine what type of equation they've got. Because once they know that, then they'll know what technique they need to solve it. Now, we don't actually solve the equations in our show. We just decide what type of solution technique to use, because that's half the battle. Now, let's meet our contestants. First, He's a farmer from Marina, Idaho. Let's meet Mr. Cletus McCoy. Cletus's opponent today is a stewardess hailing from San Francisco, California. Meet Miss Tina Grobovich. Okay, let's begin. Everyone, look at the big screen for our first differential equation.
The differential equation is 3x squared y minus 4x dx plus x cubed plus 2y dy equals 0.
And time's up. Okay, let's see how our contestants did. Cletus, you had, Greenland. I'm sorry, that is, not correct. Okay, Tina, you said, who is Abraham Lincoln? Oh, again, I'm sorry, that is an incorrect response. The correct response is that this differential equation is exact. How do we know? Well, look at the form. When an equation is split into two parts like this, the first thing to do is to see if the partial derivative of the first part, m, with respect to y, is equal to the partial derivative of the second part, n, with respect to x. This is the old m and n deal. Look here.
The partial derivative of m with respect to y is just 3x squared. The partial derivative of n with respect to x is also 3x squared. So these two are equal. Therefore, this is an exact differential equation, and we would use that technique to solve it.
Now, coming up on the big screen is our next differential equation.
The differential equation is dy plus 3xy dx equals x cubed dx.
Time's up. Okay, Cletus, what did you get? You said math. Oh, no, I'm sorry. Tina, you wrote pretzels. No. Let's see what the correct response is. This differential equation is linear first order. That means we need an integrating factor to solve it. How do we know? Well, it fits our form. dy dx plus p of x y equals q of x. Well, sort of. Look here.
The equation as given fits the form for a linear first-order equation plus one step. Notice that we don't have a dy dx in the first term, just a dy. If we were to divide through by dx, everything would fit the form just perfect. Don't let this little twist fool you.
Ooh, another curveball. Well, let's see if we can come up with an easy one for our contestants. Try this one. Good luck.
The differential equation is dy dx equals x times the square root of x squared plus 7 over y all times e to the y squared.
Okay, time's up. Let's see what Cletus got. Arvo. Well, an astute reference to Australian slang, Cletus, as Arvo does mean afternoon, but sorry, no, not correct. And Tina, oh, it looks like you've drawn a little airplane there. How cute. It's not correct.
I hate
you. Well, the differential equation is variables separable. Looked like a doozy, but with a few little adjustments, we can separate the variables and solve this puppy. Here's how.
Whenever you have an equation with two fractions like this one, always check to see if you can cross-multiply and separate the variables. Cross-multiplying here, we get x times the square root of x squared plus 7 times e to the y squared dx equals y dy. Now dividing by e to the y squared, we get x times the square root of x squared plus 7 dx equals y over e to the y squared dy. Now the variables are separated and the equation is all set to integrate.
Again, just a slight adjustment and a complicated equation can be harnessed and solved. Well, that's all we have time for today. Since both of our contestants failed to score any correct responses, neither will return as a continuing champion. But Cletus, Tina, you won't be leaving empty-handed. We've got some lovely parting gifts for you. Johnny, tell them what they've won.
The deluxe home version of Name That Equation for hours and hours of family fun solving differential equations in the comfort of your own home. It's the deluxe home version of Name That Equation.
And there you have it, ladies and gentlemen. We hope you enjoyed playing our game today. And remember, when facing a complicated differential equation, don't panic. Just name that equation.
Okay, enough TV. Now let's try to tackle a full-blown differential equation all by itself. First, we'll decide what type of equation we have and how to solve it, and then we'll actually solve the sucker. Are we ready? Let's go for it.
The differential equation is xy prime plus 4y equals x cubed minus x.
Okay, let's run this baby through our various types and see which one holds water.
The first type of differential equation we studied was variables separable. In our given problem, we cannot separate the variables because we can't get the x out of the first term without dividing the entire equation by x, which would contaminate the y in the second term with an x. We could go back and forth this way for a while, but we'd still come up with the same conclusion. The variables cannot be separated. So, no dice here.
The second type of differential equation we studied was the exact type. To put this equation into exact form, we need to make a few adjustments. First, rewrite the y prime as dy dx. Next, multiply through by dx. And finally, gather all the dx and dy terms together. Doing so, we end up with 4y minus x cubed plus x all times dx plus x times dy equals 0.
Remember, with the exact form, we labeled the dx part m and the dy part n. Then we took the partial derivative of each of them with respect to the opposite variable. In other words, we took the partial derivative of m with respect to y, and the partial derivative of n with respect to x. If the two are equal, then we've got an exact differential equation. It's that simple.
In our equation, m equals 4y minus x cubed plus x, and n equals x. Now, taking the partial derivative of m with respect to y, we get 4. Taking the partial derivative of n with respect to x, we get 1. Since 4 doesn't equal 1, the partial derivative of m with respect to y doesn't equal the partial derivative of n with respect to x. Therefore, this equation is not exact and we can't use this method.
Well, we're down to our last type of differential equation, the linear first-order type, which we solved with an integrating factor. Let's hope this one pans out.
For linear first order, the equation must be in the form dy dx plus p of x equals q of x. Notice here that if we just divide through by x, we're all set. We can replace y prime with dy dx, and we're left with dy dx plus 4 over x times y equals x squared minus 1. This is now in the proper form. There's our dy dx, and we can easily identify p of x and q of x. P of x is 4 over x, and q of x is x squared minus 1. So we've definitely got a linear first-order differential equation here.
Now that we've decided we're dealing with a linear first-order differential equation, the first thing we need to do is determine the integrating factor. Recall that the integrating factor is formed from a blob of primordial slime.
Actually, the integrating factor I of x is formed by raising e to the integral of p of x. Since p of x is 4 over x, our integrating factor is e to the integral of 4 over x dx. The integral of 4 over x equals 4 times the natural log of x. Now, remember the rule that says that e to the natural log of x is just x, and e raised to 4 times the natural log of x equals x to the 4th power. So, our integrating factor is just x to the 4th power.
Now that we've got the integrating factor, the next step is to multiply both sides of the equation by it.
Multiplying by x to the 4th, we get dy dx times x to the 4th plus 4x cubed y equals x to the 4th times x squared minus 1. On the left side, notice that we have a product rule for y times x to the 4th. See here, derivative of the first, dy dx, times the second, x to the 4th, plus the derivative of the second, 4x cubed, times the first, y. So we just write the left-hand side as the derivative of y times x to the 4th. We use the prime sign to indicate the derivative. On the right side, we distribute the x to the 4th through and get x to the 6th minus x to the 4th. Now we're ready to integrate.
Upon integrating, we just get y times x to the 4th on the left, because the integral and the derivative cancel each other out. On the right, using the power rule for integration, we get 1/7 x to the 7th minus 1/5 x to the 5th plus c. we put the solution in explicit form by dividing through by x to the fourth. This gives us a general solution of y equals 1/7 x cubed minus 1/5 x plus c times x to the negative 4.
Hey, if you got a general solution of y equals 1/7 x cubed minus 1/5 x plus c times x to the negative fourth, then you got the right answer, and you'll probably get an A in your class. It's great, isn't it? If not, just remember that you can rewind the tape and watch all that again.
Part 3. Higher order differential equations with constant coefficients.
Section A. Higher order differential equations with constant coefficients. What's that mean?
Now that we have successfully survived first-order differential equations, it's time to tackle second and higher-order differential equations. Remember, we said that the order of a differential equation is the same as the highest-order derivative in that equation. That means for a second-order differential equation, the highest-order derivative is a second derivative.
In solving higher-order differential equations, we're not just looking for one solution. For a second-order differential equation, there will be two solutions that satisfy the equation. For a third-order differential equation, there will be three solutions that satisfy the differential equation. So, what we're looking for now is a set of solutions, each of which satisfy the differential equation.
This set of solutions also has a special quality to it. Each solution in the set must be linearly independent. A solution is linearly independent if it cannot be written as a constant multiple of another solution to the same differential equation. Look here.
For example, let's say we have the two solutions y equals e to the x and y equals 7e to the x. These are not linearly independent because one is just 7 times the other. That's what we mean when we say one is a constant multiple of the other. So e to the x and 7e to the x are not linearly independent, they're linearly dependent. Now, if we had y equals e to the x and y equals e to the 7x, we'd have us a pair of linearly independent solutions because they are not constant multiples of each other.
Look at this equation. A times y double prime plus b times y prime plus c times y equals g of x. This is a second-order differential equation because the highest derivative is the y double prime, which is a second derivative. Now the terminology. An equation of this form is homogeneous if the term on the right-hand side, g of x, called the forcing term, is 0. An equation is non-homogeneous if the forcing term g of x is non-zero.
And more terminology. An equation of this form has constant coefficients if the coefficients, a, b, and c, are constants and not functions. Easy enough? All right, now let's put all this new terminology together and see what happens.
Section B. Solutions of second-order homogeneous differential equations with constant coefficients.
Here's a neat fact for you. Solutions of second and higher-order homogeneous equations with constant coefficients usually involve exponential functions, like e to the x. Take the second-order homogeneous equation with constant coefficients y double prime minus y equals 0. What we're looking for here is a function y, such that its second derivative minus itself equals 0.
Since this is a second-order differential equation, there will be two y's that satisfy the equation. Think about it this way. If you've got a second-order differential equation, there will be two linearly independent solutions, two y's that satisfy the equation. For a third-order differential equation, there will be three linearly independent solutions, or three y's, and so on and so on.
So, this equation, y double prime minus y equals 0, will have two linearly independent solutions. Like we said, many solutions of higher order differential equations involve exponential functions. So let's try y equals e to the x as a possible solution. The first derivative of e to the x is just e to the x. The second derivative is also e to the x. Plugging this into the equation gives us e to the x minus e to the x, which is 0. So e to the x is one solution. But remember, since this is a second-order differential equation, we've got one more solution to find.
For the second solution, let's try e to the negative x. The first derivative of e to the negative x is negative e to the negative x. Differentiating again to get the second derivative, we get e to the negative x again. Plugging this into our equation gives us e to the negative x minus e to the negative x, which is 0. so e to the negative x is also a solution.
Now that we have two linearly independent solutions, y equals e to the x and y equals e to the negative x, how do we express the general solution of this differential equation?
The general form for a solution to a second-order differential equation is y equals c1 times the first solution plus c2 times the second solution. c1 and c2 are the constants of integration. So, once you find the two linearly independent solutions, just fill them into this form and you have your general solution. This is called forming a linear combination of the independent solutions.
So for our differential equation y double prime minus y equals 0, the general solution would be y equals c1 times e to the x plus c2 times e to the negative x, where c1 and c2 are constants.
Now, look closely at the solutions we just got, e to the x and e to the negative x. These are essentially the same, except for the coefficient of the x that e is raised to. In general, we look for solutions of the form y equals e to the m times x, where m is a constant to be determined.
Okay, so now we know that we're supposed to be looking for solutions in the form y equals e to the mx. In our example, it was easy to figure out what values for m would work as solutions to the problem. We just picked a value and tested to see if it would work. This is a little like trying to find a needle in a haystack, especially when you start trying to solve much more complicated equations. Let's see if we can find a way to find values for m a lot quicker.
Now hold your horses there. I think I've just about got it. Nope, that's just Jimmy Hoffa.
Using the standard equation of this type, a times y double prime plus b times y prime plus c times y equals 0, we can derive a special formula for solving these types of equations. To do so, we plug y equals e to the mx, which is the general solution form, into the standard equation. And to do that, we've got to find the first and second derivatives of e to the mx.
Taking y equals e to the mx and differentiating once, we get y prime equals m times e to the mx. Differentiating again, we get y double prime equals m squared times e to the mx. Now we can plug all this junk into the equation and see what we get.
Plugging y and its derivatives into the differential equation, we get a times m squared times e to the mx plus b times m times e to the mx plus c times e to the mx equals 0. Notice that we can easily factor out an e to the mx. Since e to the mx can never equal 0, it follows that a times m squared plus b times m plus c equals 0. You may not yet realize it, but what we have just come up with is a very special equation.
This equation, am squared plus bm plus c equals 0, is called the auxiliary or characteristic equation of the given differential equation. The roots of the characteristic equation, called the characteristic roots, give us the values of m that we need to find specific solutions of the type y equals e to the mx. Remember from algebra that we find the roots of an equation by factoring the equation and setting each factor equal to 0. Of course, if you can't factor, then use the quadratic formula.
Now, if we compare our original differential equation, ay double prime plus by prime plus cy equals 0, with our characteristic equation, am squared plus bm plus c equals 0, an interesting pattern emerges. Notice that in the characteristic equation, y and its derivatives are replaced with an m of equal degree. For example, y double prime becomes m squared, y prime becomes m, and y just becomes 1. This is true for all differential equations we'll be solving using this technique.
The differential equation is 3y triple prime minus y double prime minus 8y prime plus 4y equals 0. To form the characteristic equation, we just replace the y triple prime with an m cubed, the y double prime with an m squared, and the y prime with an m, and the y with a 1. This gives us 3m cubed minus m squared minus 8m plus 4. And that's the characteristic equation.
See how easy it is to find a characteristic equation?
Okay, here's where we are so far. Solving a second-order differential equation will give you a set of two linearly independent solutions. A linearly independent solution is one that cannot be written as a constant multiple of another solution to the same differential equation. The general form for a solution to a second-order differential equation is y equals c1 times the first solution plus c2 times the second solution. The solutions are of the form y equals e to the m times x, where m is a constant to be determined.
The first step in solving a second or higher order differential equation is to find the characteristic equation. The characteristic equation is found by replacing y and its derivatives in the differential equation with an m of equal degree. The roots of the characteristic equation, called the characteristic roots, give us the values of m that we need for the specific solutions of the form y equals e to the mx. And that's where we are. Now, here's where we're going.
Okay. For a second-order differential equation, the characteristic equation will be a simple quadratic that will give us three possible outcomes when we solve it. First, we could get two distinct real roots, like 1 and -1. Second, we could get repeated roots, like 1 and 1. And third, we could get a pair of complex roots, like 2 plus and minus 3i. Complex roots always come in conjugate pairs, like this, with the plus and minus. And remember, I represents an imaginary number. But we'll get into that in a minute. Let's look at each case in turn.
The first case scenario is a characteristic equation that has two, count them, two distinct real roots. This is the most straightforward case. Here's an example. Let's solve the differential equation y double prime plus 6y prime plus 5y equals 0.
The first step here is to identify the characteristic equation for this differential equation.
To identify the characteristic equation, we simply convert the y terms to m terms of the same degree. Y double prime becomes m squared, 6y prime becomes 6m, and 5y just becomes 5. So the characteristic equation is m squared plus 6m plus 5 equals 0. Now let's find the roots of this Watusi.
To find the roots of this polynomial, we can factor the equation into the quantity m plus 1 times the quantity m plus 5. Setting each factor equal to 0, we get m equals -1 and m equals -5. These two values for m will give us two solutions for the differential equation.
So, now we got m values. What do we do with m values? Well, we plug them into our general form, y equals e to the mx. That's how we get our solutions to the second-order differential equation.
Plugging the m values we just got, -1 and -5, into the form y equals e to the mx gives us the two solutions e to the -x and e to the -5x. Putting these two solutions into a linear combination gives us y equals c1 times e to the -x plus c2 times e to the -5x. Again, don't forget those arbitrary constants. Since this is a second-order differential equation, there's two of them.
So the general solution to this differential equation, y double prime plus 6y prime plus 5y equals 0, is y equals c1 times e to the -x plus c2 times e to the -5x. That's all there is to it.
The next possible outcome when factoring a characteristic equation is that you get repeated roots. A repeated root is a root of the equation that you get more than once. For example, let's say that after factoring a characteristic equation, we got m equals -1 and m equals -1 as the roots. We got -1 twice. That's a repeated root.
If we formed a solution with these roots, as we did in the last case, we would get y equals c1 times e to the -x plus c2 times e to the -x. This is a problem. We don't have two linearly independent solutions. What does that mean? Well, look. We can factor an e to the -x out here, leaving c1 plus c2 times e to the -x. Since c1 and c2 are both constants, this can be rewritten as k times e to the -x, where k is a constant. So we really only have one solution here, k times e to the -x.
And that's not going to do it for us. We need two linearly independent solutions.
There's actually a very simple way to solve this problem. When we have repeated roots, we take the second independent solution as x times the first solution. In other words, just multiply the second solution of the pair by x. This seems like a cockamamie thing to do, but it solves the repeated root situation and also works as a solution. Watch.
In this example, we have repeated roots, and that gives us only one linearly independent solution, y equals k times e to the negative x. To get a complete solution, we multiply our solution, e to the negative x, by x, which gives us the second linearly independent solution. The complete solution to this example is y equals c1 times e to the negative x plus c2 times x times e to the negative x.
Well, that calms my nerves.
Well then, here's another one. Find the general solution of the differential equation y double prime minus 2y prime plus y equals 0.
As always, the first step here is to find the characteristic equation. To do this, we just replace the y's and y primes with m's of the same degree. So y double prime becomes m squared, minus 2y prime becomes minus 2m, and y just becomes 1. That gives us a characteristic equation of m squared minus 2m plus 1 equals 0.
The next step is to find the roots of the characteristic equation by factoring. This polynomial easily factors into m minus 1 times m minus 1. So m equals 1 and 1. Plugging into the exponential form, y equals e to the mx, gives us two solutions of y equals e to the x and y equals e to the x. We can't get the general solution from this because we've got repeated roots.
Well, I guess we'll have to multiply by x.
That's right. Since we have repeated roots, we multiply the second root by x to obtain the second solution. So our linearly independent solutions are y equals e to the x and y equals x times e to the x. So the complete general solution for the differential equation y double prime minus 2y prime plus y equals 0 is y equals c1 times e to the x plus c2 times x times e to the x.
Here's a question. How can we check to see that we have a correct solution to the differential equation? In particular, does y equals c1 times e to the x plus c2 times x times e to the x satisfy the given differential equation y double prime minus 2y prime plus y equals 0? We can check by plugging our solution into the differential equation. So let's do that now.
Before we can plug in our solution, we need to find its first and second derivatives. Starting with y equals c1 times e to the x plus c2 times x times e to the x, and differentiating, we get y prime equals c1 times e to the x for the first term. Then, using the product rule, we get plus c2 times 1 times e to the x plus x times e to the x. This simplifies to c2 times e to the x plus x times e to the x. So the first derivative is c1 times e to the x plus c2 times e to the x plus x times e to the x.
Likewise, to get y double prime, we differentiate again and get c1 times e to the x plus c2 times e to the x plus 1 times e to the x plus x times e to the x, or just c2 times 2e to the x plus x times e to the x for the second part. So the second derivative is c1 times e to the x plus c2 times 2e to the x plus x times e to the x.
Plugging these into the original differential equation, y double prime minus 2y prime plus y equals 0, we get this unbelievably long mess here. Combining like terms, we get 2c1 times e to the x minus 2c1 times e to the x plus 2c2 times e to the x minus 2c2 times e to the x plus 2c2 times x times e to the x minus 2c2 times x times e to the x equals 0. Now watch this. The 2c1 e to the x's cancel each other out, as do the 2c2 e to the x's and the 2c2 times x times e to the x's. We're left with 0 equals 0, and the last time I checked, 0 does equal 0, so this one checks out.
As you can see, we're not full of hooey here because these things actually check out. This is a good way for you to check your answers on any of your problems. Just plug the solution into the original differential equation and see if it's satisfied.
That concludes our section on repeated roots. They sure are something, aren't they? Kind of reminds me of when I repeated 10th grade. But that's another story.
So far, we've looked at differential equations with 2 distinct real roots and 2 repeated roots. Now, let's move on to the last case that you'll encounter when solving a characteristic equation: pairs of complex or imaginary roots.
Okay, let's get down to business. You may be asking yourself, just what are complex or imaginary roots? Well, a complex root takes the form m equals a plus or minus bi, where I is the square root of -1. Complex roots of real quadratic equations always come in pairs. Because of this, mathematicians and other smart people like to call them conjugate complex roots.
Just where do these complex roots come from? Well, you get them when you got to take the square root of a negative number when finding the roots of an equation. One place this happens all the time is with the quadratic formula.
The quadratic formula looks like this. X equals -b plus or minus the square root of b squared minus 4ac all over 2a. You need to use the quadratic equation when you can't factor a second-degree equation by the normal means. If you are left with a negative number under the radical sign, then you're going to get a pair of these ugly complex roots. Here's a quick memory refresher.
Suppose you have the differential equation y double prime minus 4y prime plus 13y equals 0. The characteristic equation is m squared minus 4m plus 13. We can't factor this the normal way, so we need to use the quadratic formula.
Note to self, make doctor's appointment for Wednesday.
For the purposes of the quadratic formula, a equals 1, b equals -4, and c equals 13. Plugging this into the old formula, we get m equals minus -4 plus or minus the square root of -4 squared minus 4 times 1 times 13 all over 2 times 1. This simplifies to 4 plus or minus the square root of -36 all over 2. The square root of -36 is 6i. Now dividing by 2, we get roots of 2 plus or minus 3i. And those are complex conjugate roots, if you ask me.
Okay, so now we know where those complex roots come from. But now that we've got them, what do we do with them?
Using a formula invented by a guy named Leonhard Euler, it can be derived that roots of the form m equals a plus and minus bi gives the linearly independent solutions y equals e to the ax times the cosine of bx and y equals e to the ax times the sine of bx. Putting these two solutions together in a linear combination gives the general solution y equals c1 times e to the ax times the cosine of bx plus c2 times e to the ax times the sine of bx.
We could take you through a long and tedious derivation of this formula, but for our purposes, it's really not important. I'm sure it's important to Euler, but ever since he came up with his own special formula, he's been awfully demanding. So we'll just leave that part out.
In our little example here, with roots of 2 plus or minus 3i, we see that a equals 2 and b equals 3. Plugging these values into Euler's formula, we get y equals c1 times e to the 2x times the cosine of 3x plus c2 times e to the 2x times the sine of 3x. Do you see how that works? Well, here's another example for you.
Okay, let's solve the differential equation y double prime plus y equals 0.
Our first step is always to find the characteristic equation, which in this case is m squared plus 1 equals 0. Solving for m, we get m squared equals -1, or m equals plus or minus the square root of -1. Since the square root of a negative number is an imaginary number, we get a solution of m equals plus or minus I.
Comparing our roots of m equals plus or minus I to the general form, m equals a plus or minus bi, we see that a equals 0 and b equals 1. Plugging this into our formula for the general solution, y equals c1 times e to the ax times the cosine of bx plus c2 times e to the ax times the sine of bx, we get y equals c1 times e to the 0x times the cosine of x plus c2 times e to the 0x times the sine of x. Since e to the 0x equals 1, our general solution is just y equals c1 times the cosine of x plus c2 times the sine of x.
We can check to see that this solution is correct the same way we did before. Just plug the solution into the original equation, y double prime plus y equals 0. Remember, you need to find the second derivative of the solution to do that. We won't go through it all here because we're pretty sure that we're right. But if you'd like to have that same inner conviction of correctness, check it out and see what you get.
That was a relatively simple example where it wasn't necessary to use the quadratic formula, but it makes the point. The basic method is the same. Identify the characteristic equation, find the roots, and combine them into a solution based on the type of roots you get. Before we go on, let's pause and review each of the three cases.
To solve a second-order differential equation, we first find the characteristic equation. The characteristic equation is formed by replacing y and its derivatives in the given differential equation with an m of equal degree. Factoring the characteristic equation, or using the quadratic formula to find the roots, will result in one of three possible outcomes. There could be two distinct real roots, repeated roots, or a pair of complex roots.
If the equation has two distinct real roots, we just plug those m values into the form y equals e to the mx to get the two solutions. The general solution takes the form y equals c1 times the first solution plus c2 times the second solution, where c1 and c2 are constants of integration. If the equation has repeated roots, we take the second independent solution as x times the first solution. We then put the two solutions into the general solution form y equals c1 times the first solution plus c2 times the second solution.
If the equation has a pair of complex roots of the form m equals a plus or minus bi, then we use the form y equals e to the ax times the cosine of bx and y equals e to the ax times the sine of bx as the linearly independent solutions. The general solution then takes the form y equals c1 times e to the ax times the cosine of bx plus c2 times e to the ax times the sine of bx. And that's what you need to know. Whew!
Section C, solutions of higher-order differential equations with constant coefficients.
So far, we have covered first-order and second-order differential equations. As you may have noticed, there is a big difference between solving first and second-order differential equations. But what about third-order and higher-order differential equations? Is there a whole new, different way to solve those types of equations?
Separate the variables.
Get a new line, all right? Actually, we can solve higher-order homogeneous differential equations with constant coefficients the same way we solved second-order homogeneous differential equations with constant coefficients. Remember those? Those are the ones we just did in the last section.
In other words, we solve third, fourth, and fifth-order differential equations with the characteristic equation method as well. Only now, since there are more than just two linearly independent solutions for each equation, we can end up with a combination of real, repeated, or conjugate complex roots of the characteristic equation. Here's an example to show you what we mean.
Let's solve the fourth-order differential equation, the fourth derivative of y plus 2y double prime plus y equals 0. Finding the characteristic equation, we get m to the fourth plus 2m squared plus 1 equals 0. This equation can be factored into m squared plus 1 times m squared plus 1 equals 0.
Setting each factor equal to 0 to find the roots, we get m squared plus 1 equals 0, or m equals plus or minus the square root of negative 1. Therefore, m equals plus or minus I. Since both factors are the same, we have two sets of the same solution. This gives us a total of 4 solutions for the fourth-order characteristic equation. Makes sense, right? Fourth-order differential equation, 4 solutions. They are m equals plus and minus I, and m equals plus and minus I.
Notice that what we've got on our hands here is a group of roots that are both complex and repeated. To deal with this fiasco, we employ the rules for both repeated roots and for conjugate complex roots.
First, let's recall the rule for conjugate complex roots, since we've got a couple of them here. We said earlier that a root of the form m equals a plus or minus bi gives the linearly independent solutions y equals e to the ax times the cosine of bx and y equals e to the ax times the sine of bx.
Comparing our roots of m equals plus or minus I to the general form, m equals a plus or minus bi, we see that in our case a equals 0 and b equals 1. Plugging these values into the formula here, we get y equals e to the 0x times the cosine of x and y equals e to the 0x times the sine of x. Since e to the 0x equals 1, we end up with the two linearly independent solutions, y equals the cosine of x and y equals the sine of x. But this is only half of our solution set.
Since the roots m equals plus or minus I are repeated, we need to go back to our repeated root rule, which says that we multiply the solutions related to repeated roots by x. Doing this, we get two other linearly independent solutions, y equals x times the cosine of x and y equals x times the sine of x. Putting all four of our solutions together in a linear combination gives us y equals c1 times the cosine of x plus c2 times the sine of x plus c3 times x times the cosine of x plus c4 times x times the sine of x as the general solution to this here differential equation.
So, higher order differential equations of this type follow the same rules as their second order counterparts. The only exception is that we now sometimes have to combine the rules just to solve one problem.
Also notice that it gets kind of hairy trying to find the roots of a higher order characteristic equation. Sometimes you may not be able to identify factors just by eyeing the equation. One method that sometimes works is synthetic division. Remember synthetic division?
Look at this example. Solve the third order differential equation y triple prime minus 3y double prime plus 3y prime minus y equals 0.
Converting to the characteristic equation, we get m cubed minus 3m squared plus 3m minus 1 equals 0. Just looking at this thing, you should be able to tell that you can't just outright factor it. One way to factor this is with synthetic division.
To use synthetic division, we need to make ourselves a little table. First, we write down the coefficients of each term on the top line. Then, we need to choose a special number for the box. For the box, we choose a number that is made up of factors of the last term, -1, over factors of the coefficient of the first term, 1. So, in our case, our only options are plus and minus 1. Let's try 1. Put that in the little box, and we're ready to begin.
Now that we're all set, we start by bringing down the first 1, multiplying that by the number in the box, which gives us 1. We put that 1 under the -3 and add, getting -2, which we write here. Multiplying again, we get -2. Adding, we get 1. Multiplying again, we get 1. And adding, we get 0.
Since we got a remainder of 0, this means the number in the box, 1, is a solution of the characteristic equation. Now, we were lucky and found a solution on our first attempt. You will probably need to try a few choices before you find one that works. At any rate, our solution forms a factor, m minus 1. The remaining factor is made up of the numbers on the bottom row, 1, -2, and 1. Just add descending powers of m, starting with m squared. So the second factor is m squared minus 2m plus 1.
Notice that we can factor the second term into m minus 1 times m minus 1. This leaves us with 3 identical factors of m minus 1. And you know what that means?
Repeated roots!
That's right. We've got 3 roots. M equals 1, m equals 1, and m equals 1. Because we have 3 repeated roots, the linearly independent solutions of the differential equation are e to the x times e to the x, and x squared times e to the x. So, the general solution is y equals c1 times e to the x plus c2 times x times e to the x plus c3 times x squared times e to the x.
Remember, we can check that the solution satisfies the given differential equation by plugging it and its derivatives back in.
Again, it's the same old method. Identify the characteristic equation, find the roots, blah, blah, blah. It's just that sometimes these problems can be booby-trapped and put you into a situation where factoring isn't quite so simple. That's when we have to remember all our algebra techniques of old, such as synthetic division and the quadratic formula. That's the thing about math. It just keeps building on itself, so you can't forget what you learned.
Section D. Non-homogeneous differential equations with constant coefficients.
We now turn to the class of non-homogeneous differential equations with constant coefficients. Remember how we defined a non-homogeneous differential equation earlier? All right, we'll tell you again.
Look at this equation. A times y double prime plus b times y prime plus c times y equals g of x. This equation is homogeneous if the term on the right-hand side, g of x, called the forcing term, is 0. On the other hand, the equation is non-homogeneous if the forcing term, g of x, is non-zero.
So the main difference between homogeneous and non-homogeneous equations is all in the term on the right-hand side. If that term is 0, then we've got a homogeneous equation on our hands. If it's something else, like a constant or a function or a hibachi grill, then it's non-homogeneous.
Because homogeneous and non-homogeneous equations are so close, the approach to solving them is also very close. Actually, the method we used for solving a homogeneous equation in the last section is the first part of the method we'll use here to solve non-homogeneous equations. Didn't we tell you this stuff all builds on itself?
The complete solution of a non-homogeneous equation has two pieces. There is a complementary solution, y sub c, which is the solution of the corresponding homogeneous differential equation. In other words, we take our non-homogeneous equation and make it homogeneous by dropping the function g of x on the right side and sticking 0 in its place.
The other piece is called the particular solution, y sub p, which makes up for the missing in action function g of x. Therefore, the complete solution of a non-homogeneous differential equation is the combination of the complementary solution plus the particular solution. Y equals y sub c plus y sub p.
This all may sound confusing right now, but in practice it's not that bad. Finding the complementary solution, y sub c, is the same thing we just did before with homogeneous equations. We've already got that part down.
So, finding y sub c isn't that tough. We just do all the stuff we did before. Find the characteristic equation, factor it, put the roots into the form for the general solution, blah, blah, blah. It's the y sub p that's gonna give you headaches. In order to find y sub p, we use a method called the method of undetermined coefficients.
Just like everything in this videotape, the method of undetermined coefficients sounds a lot more